Hello everyone. So today we'll be solving the problem 201 bitwise and numbers range. Basically bitwise and of the numbers range. Sorry, not and bitwise and of the numbers range. Right. So what the question states here? Let's see. Given two integers left and right. So see here we are given two integers here left and right that represent the range left comma right. Basically we have been given two integers left and right that represent the range left comma right. So what we need to do here, we have to return the bitwise and of all the numbers in the range that is inclusive. What we need to do, we have to return the bitwise and of all the numbers in this particular range that is inclusive. Let's get into the example part, man. The first example here. So input we have the left 5, right 7. The output that we need to get here is 4 basically, right? So again, left and right we have been given represents the range basically from 5 to 7, right? So we have to return the bitwise and of all the numbers in this range from 5 to 7, 5, 6, 7. We have to this one, what do we call? I return the bitwise end of all the numbers in this range. For this one particularly, we get the output 4. We have 0, 0. Whenever we have been given 0, 0, we can just directly write 0 output, right? So left we have been given 1, right we have been given this number, output is 0. Let's see for this one example. Let's consider this example for the approach so that you can implement the same thing for the example 2 as well as the example 3. They've given us wonderful examples here, right? So let's consider this one for the approach. First, let's discuss the approach, then followed by the complexities, and then let's write the code, right? So first let's discuss the approach. Just give me a second here. 1 second, man. Yep. So let's do one thing. First, let's go with the approach part here. So we'll be going with a bit manipulation as I've said. So to solve this particular problem, we'll be making use of the bit manipulation, right? So this is fine, man. We have the left 5, right equals 7. We are considering the first example here. So first thing is we will be writing the binary of 5 and binary of 6. So what is the binary? We'll be converting 5 and 6 to the binary. So what is the binary of 5? You can just Google this one. So this is 101 and the binary of 6 is 110, right? So and 567 basically 7 also we are going, right? 567 because it is in the range from 5 to 7 basically. So they have been given in the question that we have been given two integers left and right that represent the range, this one left to right. So we have been given the range 5 to 7 which consists of 5, 6, 7, right? So this is the range basically, three numbers. So this one 7, 6 we have written this one, what do we call, 110, and the 7 is represented as 111 in the binary, right? So now bitwise and of 567 removes any bit that differs across this particular range, right? So this is the approach basically. This is the first point. Let's move on with the second point here. What we will be doing, we will shift the both ends right until they match, right? So first what we will do, we will shift 0. I'll just write here S0. We'll shift 0. Nothing but we will go with the left shift, right? So this one will be left. So this one will be 101, nothing but 5. And for the right, we consider here this one 111, nothing but the 7 here, right? So these are not equal. These are again not equal, not equal. I'll just write here NE, right? So this is fine. Next step, this is the first step, right? So second step would be we will be shifting 1 basically, right? So we will be shifting 1 left. We have 10, nothing but the 2, and left we have only 10, nothing but the 2, and the right we have 1, 1. We are shifting the shifting left, right? So this one we have considered the last digit already. So 1011 will be going. So 11 is nothing but 3 in the this one, right? 3 in the normal digits basically. So this is also not equal, right? So this is also not equal. Next, let's go with the shifting 2 basically. Now left is 1 and right is 1. So this 0 is gone. We are shifting right. So this 1 is gone. We are left with only 1 and 1 here. Left is 1, right equals 1 here, right? So this is in digits it is 1, and digits it is 1, right? So this is equal. Now this is equal basically, 1 and 1. This is equal. So we removed two last significant bits. So here we removed 1 and 1 left and right. Here we removed 0 and 1. This is fine. What we removed? We removed two this one least significant bits or LSBs, right? So we removed two least significant bits, right? So 1 and 1 are equal. Now the common prefix here is 1, right? So this one. Now the common prefix here is 1. So let me write here common prefix here. So let me write C for the prefix we have is 1 here, right? So we will shift it back left by 2, right? So now what we will do for 1, when we shift back, so this one we will be adding 2 zeros, right? So the common prefix is 1, we will shift it back left by 2. So this will be 100. So 100, we are representing this one in the form of binary. When we convert to the digit, it will be 4 basically. You can just check. It is 4, right? So basically this is the result. The output that we got here is 4, right? And the normal digits. The output that we got here is 4, which is equivalent to the output that they have shown for the example 1 within the question. So our approach works absolutely correct here. So the same thing you can just check it for the example 2. Example 2, they have given both zeros. So you'll get this one directly. You can just check for the example 3. I insist you to check for the example 3 or any. You can just take the custom example and you can just check, right? So here the output that we got here is 4, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So our approach works absolutely correct here. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part, right? So let's quickly discuss the complexities part and then let's write the code. So what will be the time complexity here? Let me remove this one entirely. So what will be the time complexity? The time complexity is big of 1. So why it is big of 1 here? So whatever the loop that we'll be considering, it runs at most 31 times for the 32-bit integers, right? So this is constant time. So time complexity would lead to big of 1. So what would be the space complexity here? The space complexity would lead to big of 1 as well, because we'll be going with only a fixed number of integer variables that will be that are being used here. So the space complexity would be big of 1 as well. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of 1 and big of 1 respectively. Now, as we are completely familiar with the approach and the this one, what do we call complexities, we are good to write the code. Let's start writing the code, right? So let's do one thing at the beginning. Let's go with the shifts, man. Nothing but the result variable, right? So this counts how many least significant bits that we remove, that are removed or that we remove, right? So here I'll just go with a shift. So let's implement the same thing that we have discussed in the approach. Shift equals 0. We're just initializing the shift counter to 0. Now let's write the standard while loop left less than right. Then what we'll be doing? So we have to keep removing the least significant bit from the both sides, both ends. Basically, that's what we saw in the approach, right? By considering the first example, I showed you the same. So we have to do it until the remaining higher order bits prefix becomes identical or same. So at last we got 1 1 which were identical or same, right? The value was same basically, right? So here the loop runs at most 31 times. We are making use of the while loop. This loop runs 31 times for the 32 bits non-negative, this one ends, right? So this is fine. Within this one first, so let's go with the unsigned right shift, that is left by 1, right? So that's what we did at the first step. Second step also we'll be doing the same thing, but for the second step it will be going with the left and right, right? Unsigned right shift, unsigned right shift left by 1, unsigned right shift right by 1. We'll be dropping left's LSB, nothing but the least significant bit. Also we'll be dropping right's least significant bit, nothing but the LSB. So I can just represent this one in this way. Left equals 1. Also let me go with right shift, one right shift operator we have to make use of. This is 1. Now let's increment the shifts, right? So let me increment the shift. So this one is we are just removing one differing bit position here, right? So finally we are done with the code. Finally what we need to do, so we have to restore the removed bits by left shifting the shifts times, right? So that's what we saw in the approach. So I'll just go with left here. Left shift, shift is the variable we made use of, right? Yep. basically. Yep. I have given shift here. I have used shifts everywhere. Let me consider this one as shifts itself. Right, this is fine. Let me format the code once and let me hit the run button. So here the sample test cases are getting passed, means the code works absolutely correct for the example test cases. Let's see. Let me hit the submit button. I hope this works for all the test cases. Yep, this works for all the test cases, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.